So this is the big pulley assessment. In this situation, we have a large pulley which has a 50-gram weight attached to the left side and a 200-gram weight attached to the right side. The pulley weighs 1 kilogram and the radius of it is 0.1 meters. First thing we want to do is draw a force diagram for each piece of this puzzle. So we have 3 objects. The first one, we have the Earth pulling down with a, we'll call it M1G, small, and we have tension pulling up a little bit more than this M1G because we know it's going to be accelerating up. So tension 1 we'll call it. The other one, we have M2G because it is heavier, and we have the tension pulling up with less force because we know that there's going to be an unbalanced force down. In this third example, or in the disc, we have the T1 pulling down on this side and the T2 pulling down on the other side, and these are just the same as in here. First thing we want to do is calculate the acceleration of the masses. In order to do this, we need to use the find an equation for the tension of this for T1, tension of this T2, and then use the inertia concept to relate those two tensions and the rotational acceleration of the pulley to find the acceleration of the masses. So start out with mass 1. We know our F net is equal to M1A, and our F net 1 also equals tension 1 minus M1G from our force diagram. So we can say M1A equals tension 1 minus M1G, and then we can rearrange this and get tension 1 equals M1A plus M1G. So that's great. For our second mass 2 we'll call it, we know our F net 2 equals M2A, and our F net 2 equals M2G minus T2. So we can say M2A equals M2G minus T2 from our force diagram. And then we can rearrange this and get T2 equals M2G minus M2A. Next thing we need to do is use torque concept. So we're going to say our net torque, because there is torque on this disk, torque net is equal to the inertia of the object times its rotational acceleration, which we express as alpha. And torque net is also equal to the distance the torque is applied times T2, and then we would also say times the sine of the angle, but since it's at a 90-degree angle relative to like a flat plane, it's going to be sine of 90, and that's going to be 1. So T net is just going to be RT2 squared, or RT2 minus RT1. And then so we can say I alpha equals RT2 minus RT1. So we know linear acceleration equals R alpha, and we can rearrange this and express alpha in terms of linear acceleration. So alpha equals A divided by R, and then if we Google on the internet for a solid thin disk, inertia is going to be 1/2 mr squared, m being the mass of the pulley. So we've got this. Now we just got to take all these pieces, these two, and put them into this equation. So I'm going to erase some things to do that. That. We're going to say 1/2, so I alpha, 1/2 mr squared, and then we're expressing alpha as a over r, is going to equal rt squared minus rt1. So we'll get rt2, I mean, rt2 is m2g minus m2a, and then the other one, rt1, is going to be minus r, and then m1a plus m1g. So now we have plugged in everything. We can erase our extra pieces. We can do a few things with our r's. Over here we have a r squared and an r in the denominator, so we can get rid of the squared and get rid of this r. And then we also have an r in each piece of the equation, meaning we can get rid of the other r as well. So that makes it a little bit easier to work with. So we'll get 1/2 ma equals m2g minus m2a minus m1g minus m1a, because we are distributing that negative to the positive. We can rearrange this. We're going to try and take out all of the a's and factor it out so we can solve for a. So we're going to move all the a's to one side. 1/2 ma plus m2a plus m1a equals m2g minus m1g. Factor out the a, we'll get a equals 1/2 m plus, or no, a, then parentheses, 1/2 m plus m2 plus m1 parentheses equals m2g minus m1g. Run out of space again, but we're just plugging and chugging at this point almost. Don't really need this. We're going to say a equals, we're going to move this to the denominator the other side, so we'll say m2g minus m1g divided by 1/2 big M plus m2 plus m1. Then we can just plug in everything. We just get a equals m2g, this is going to be 0.2 times 10, gives us a 2, minus a 0.05 times a 10, which gives us a 0.5, over a 1/2 big M, and since big M is 1, it'll just be 1/2, plus m2, which we know is 0.2 kilograms, plus m1, which we know is 0.05 kilograms. So A will equal 2 meters per second squared, because it is an acceleration value, and that applies to the acceleration for the entire system, just not rotational acceleration for this pulley. The next question we have is to calculate the tension in the strings. So we know from before we had our tension formulas from our first mass and our second mass, which I'm rewriting right here. They were tension 1 equals m1a plus m1g, and tension 2 equals m2g minus m2a. So now we know our linear acceleration, so we know our masses. All we got to do is choose one and plug in numbers. I'm going to choose tension 1, we'll say tension 1 is equal to M1, which is 0.05 times A, which we got as 2. My marker's not working. That marker does not work. 2, and then a plus another M1 times G, which is 10. So we'll get tension 1 equals right here we're going to get 0. Let's see, this is going to be 0.1, 0.5, yeah, 0.6 newtons in the first string, and then the second string we have tension 2 equals M2 is 0.2 times 10 minus 0.2 times 2. So that's 2 minus 0.4. Tension 2 is equal to 1.6 newtons. And that's the tension 1 here and the tension 2 here.